Often you're asked in this IB program, when do objects collide? If you're given object A somewhere, then the vector R to it can be described as vector A plus lambda B. But because we're talking about objects in the real world, instead of lambda, we're going to use t for time. And our B vector will really be velocity. We can break the B vector into the velocity of its x component of object A and the velocity of its y component also of object A. Our starting point, A, capital A, is now at x1, y1. So we can, instead of r equals A lambda B, we're just changing it slightly into r equals A plus, instead of lambda, it's t. For object B, it's r equals A lambda B. Instead of lambda, we've got t. That's going to be the proportion of vector B that we want to go down the road. If r of B is x2, y2 plus t times the vector in the x direction and the vector in the y direction. This little division sign should not be there. Well, if you can follow me that far, that this is really r equals A plus lambda B with position and velocity, and our lambda is going to be time. Well, we're asking, when do the objects collide? Well, I set r of A equal to r of B, because if they collide, then the r vectors are going to be going to the same spot. In other words, the position vector of r is going to be the same. So I set this equal to this, and then I break it into its parametric form. x1 plus t times vxa is equal to x2 plus t times vxb, and y1 plus t vyb is equal to y2 plus t vyb. I've got my two equations there. All we have to do is solve for t. If I get t equals 5 seconds here, and t equals 5 seconds here, then I can conclude that the two objects collide at 5 seconds, because both their x and y position at time equals 5 seconds are equal. In other words, from this we can conclude that the objects are in the same position at the same time. So they are shocking each other. They are colliding. Here's a problem we do with vectors often. Determining when objects collide. We do this often. Two vectors A and B have their positions defined by these vector equations. This is RA. Remember, this is a point on the line, negative 8, 3, plus this is where we're going. This is the directional vector, and this is the position vector. And RB starts at some point here, and this is its directional vector as well. We can see that if this is time, these are the time components, well then this will be a velocity vector. If this is time, this is a velocity vector, because time times velocity will give you position. Meters per second times second gives you meters. So this will be velocity, and this will be time, and this will be a position. Now t is greater than or equal to 0 and is measured in minutes, and all distances are in meters. Again, this is going to be meters, and this is the velocity, meters per second times time, also gives you meters. Well, will they collide? Remember, if this is vector A here, and this is vector B, well, or we could call this RA and RB. If they collide, then this little arrowhead and this little arrowhead will be going to the same spot at the same time. How do we determine if they're going to the same place at the same time? Well, set them equal to each other. If they're going to collide, then at some point they'll be at the same spot at the same time. This will be, this is equal to this. That's our first step in saying, do they collide? Set this one equal to this one. Once we set vector RA equal to vector RB, we can split it up into its components. Negative 8 plus t times 4 is equal to 2 plus t times 2. So I set the top equal to the top, that's sort of the x component, and 3 plus 3t is equal to negative 7 plus 5t. I set the bottom half equal to the bottom. If these vectors collide, then they'll be in the same place at the same time, and our final answers will match up. Well, when I solve for t, get all the t's on one side, all the numbers on the other, I get t equals 5 seconds. When I get all the t's on one side and all the numbers on the other, I get t equals 5 seconds. We can interpret this when we set the top equal to the top and the bottom equal to the bottom we can interpret this as, yes, the x component is in the same place at the same time as the y component is in the same place at the same time. Therefore, the two objects do collide. But these have to match up in order for them to collide.